In the last lecture we talked a little about revision of op-amps and some of the imperfections. Now we're going to look at some of the detail of imperfections within op-amps as part of our static errors section of the electronic system design course. Imperfections in op-amps, as we discussed previously, can be modelled as a perfect op-amp plus additional linear sources. And the performance of a system is always measured against the specification. ESD3 is concerned about what methods we use to connect imperfections and deal with imperfections to produce a design which can be proven to meet a specification. Our design process is very rigorous, and this is precisely the design process that I used as an industrial designer for many years in the electronics field. One of the most overriding things that you're required to do as a designer is to address and implement the specification in as low and cost-effective manner as you can. In other words, produce cheap, high-quality goods. In electronic system engineering, we've talked about how important signal conditioning is. Our goal is to produce an accurate, clean, and immune from disturbance input signal, so we can then take that signal, process it further in our system to produce the outputs in the most effective way we can. And a lot of the focus on this course is how we deal with low-level signals and errors in those low-level signals and condition them so that the system can use them. I found this quote on the internet, and it was addressed to Charles Babbage, who was the inventor of the computer. I find it quite funny that the concept that if you put wrong figures into a machine, will the right ones come out, is clearly ridiculous. And similarly, in system design, if you put the wrong or poor quality input signals into your process, you will not get high quality outputs. So let's look at imperfect op-amps, but consider it from the standpoint of perfect op-amps. A perfect op-amp produces an output signal which is equal to an infinitely high gain multiplied by the difference between the inverting and the non-inverting inputs. However, in imperfect op-amps, we have current flow that goes into the inputs. We have biases and offsets. They can be slow, they can be bandwidth limited, they could be slew rate limited, or they could have excess phase margin, which leads to instability. In all op-amps, the output has a finite impedance, but this can be reduced by feedback, and they often have various input errors. In addition to problems at the input, we can have signal modifications, mainly dynamic errors, from common mode rejection, power supply rejection, or things due to drift over time or temperature of the part. And if you want to read more detailed analysis, if you look at the book Op-Amps for Everyone, in chapter 11, it gives you a full treatise of how to do it. There's also a very good application note which you should search on the internet for by Ray Stata, and this is an application note on how to apply and measure op-amp specifications. It's very useful, and it's very useful to understand the problems that modern op-amps produce in measurement. When you're designing with imperfect components, it's vital that you specify either the system or the subsystem. You need to define the function, perhaps a gain of plus 10. You need to define the external connections. Where is the source voltage coming from? What is the source impedance? And you also need to define the performance that you expect to get. What scale, what offset errors you are willing to accept as your solution, what bandwidth the input signal and the output signal needs to be, and power dissipation. And there are many more. The specification and analysis are the key to design. And the way we address these is we go through three fairly simple but vitally important steps. Step 1, we produce what we call a naive design of the basis functionality. It's a full design. It includes a choice of op-amp and some approximate component values to deliver the function. What we suggest to do here is you start with a cheap component and then work upwards. Second, You take that naive design and you analyse the circuit for sources of error. And you identify the dominant errors, and you then focus on removing or reducing the dominant errors. And lastly, you optimise your design to get the best performance and also the minimum cost. Let's look at an op-amp and look at some of the detail. So here's a typical op-amp. It's an NE5532. It's a well-known product. Where's the input stage? Yes, it is quite complicated, isn't it? Let's try and take the circuit diagram and the schematic to pieces, and let's try and identify it. So on the left-hand side, those two transistors are connected as diodes to protect, as protection. At the top we have a diode connected as part of the bias circuit. We have two series diodes connected as a bias circuit. We have more bias circuit. This is followed by a large block which provides high voltage gain and the output stage. So the only thing that is left are these three transistors as the input stage. So let's try and look at these in more detail. So I've copied just the input stage over, and here we can see the two input transistors, and I've replaced the third transistor by a current source because that's the function it's providing. We have our two inputs and we have a differential output appearing across the two load resistors, and these get passed on to the next stage for further amplification. We're going to make some assumptions here, and the assumption I'm going to make is that Q1 and Q2 are identical. I'm not talking about looking similar. For this analysis, we are going to assume that every atom, every electron in these transistors is absolutely identical. We're also going to assume that the voltage appearing on the non-inverting or plus input and the voltage appearing on the inverting input or the minus input are identical, and they meet the requirements for virtual earth. If the two input voltages are identical, then the conditions under which Q1 and Q2 are operating must also be identical. So we must have half current going up the left transistor and half current going up the right transistor. Because the two base emitter junctions are identical voltages, therefore the collector currents must be identical. Because of the relationship associated with bipolar transistors, it also means that the current flow going into the two inputs must also be identical. So let's look at it in slightly more detail. Because we have a constant current as the tail current, defined as I0 in this diagram, because all the components are matched and the virtual earth principle is being applied, then both input currents must be the same. The input currents are equal and are independent of the input voltage if negative feedback is present. So we have constant input current. In other words, if this current and this current are both constant, then any change of voltage here will result in no change of current here and here, which means that the input impedance must still be infinite. Now note, the input current is not zero, but the change in IN equals 0.